Okay, so what if we want to transform for a rational function? Ooh. We'll make a reasonably simple one. A rational function, remember, is y is some polynomial p of x over another polynomial q of x. Okay, and so get the idea here with maybe just a couple of quadratics. So suppose I had y equals ax squared plus bx plus c over, let's see, I don't want to use d, e, and f, so I'll use r, well, how about u, v, and w, something like that, over u x squared plus v x, it's just x, plus w. So I have these 6 constants I'm going to try to figure out. Now, what you may run into is you may not be able to do this very well because you're trying to get too many constants. We'll look at that in a minute. But what you can do is to transform this to try to get something that looks a bit more linear. Multiply both sides by the denominator, and I get u x squared y plus v x y plus w y is equal to a x squared plus bx plus c. Now, actually, what you can do is you could solve for y here. So what you're really doing when you solve for y is essentially you're assuming, for the moment anyway, w equals 1. But if I solve for y, I get y equals ax squared, because see, I could have a over w, right? But we'd have to rename that. So we're really just assuming for the moment w is 1, but that's not a big deal because we could factor things out. And right, you know, I could, whatever w is, I could factor it out of the bottom here, and I could put it into a, b, and c. So not a big deal. Okay, so ax squared plus bx plus c. Now, if you know, I wouldn't have to write this as minus, but it might keep me from screwing up. Minus u x squared y minus v x y, like that. And so what that says is if I started with my columns x and y, what I need to do is add some more columns. Now y is still the response variable, or the the dependent variable, but the columns I need to add here are x squared. I need a column. Now what I might want to do is do a minus x squared y and a minus xy. And so again, this is my dependent variable, but I would give these other 4 columns to my multiple regression and just run that multiple regression and get my constants. And again, notice I'm keeping the minuses because I'm just a little worried if I don't, I'll forget to make them negative, you know, when I go to put them back into the problem. But so you see, I could, you know, and I could do this with any size rational function that I want. You know, I could go to cubes or fourths or fifths or whatever, both top and bottom. if I have some reason to believe a particular form, say a quadratic over a linear or something like that, or one quadratic over another quadratic because of the shape of the curve, I can do that and build these in. And I think I said something about if you have too much, but no, you'll be, the only thing, if you don't have enough data, I mean, you always need to do the multiple regression least squares idea. You always need more rows of data than columns, otherwise you're going to have a problem. But probably as long as you're, here we're only adding 3 new columns, and in just adding the 3 new columns, I'd say probably you'll have more data than that, so not a big deal. Okay, so that's the idea in trying to transform a rational function to fit that with least squares. So you can really, fit lots of different functions using this least squares criteria. We've hit on a few, but they're pretty versatile. I mean, by the time you hit these rational functions, in the end, if what you're just trying to do is get a function that looks a lot like your data, if you can't do it with a rational function, you probably have some pretty messed up data, because rational functions can do just about anything. Okay, so we'll call that good for transforming data for the rational functions, and there we go.